And let me know if, why is it? Okay, it has started recording. And let me know if you can see my screen. Yeah, okay. So, hello everybody. Thanks for coming to the third quantum computing session at Hackaday. We do this every Sunday, this time for 30 minutes. Today I know it's Easter. A lot of people are off, but everyone's staying at home anyways. So I hope this is fun, so people wouldn't consider this as work. The class today, we will talk about entanglement, but this is an overview of what happens in this Sunday classes. We have 30 minutes each day talking about one topic, and that topic is based on my comics of the week. If you have already followed my project on Hackaday or on social media, you know that today we're going to talk about entanglement because this is the third class. We have already covered a few basic concepts. And if you missed them, don't worry, there's the link to the Hackaday project. Also, Brian has posted it in the chat. You can follow and find the links to the recordings from before in the files section. And I also include a couple links, useful links that you can look up for your self-learning. And we also gonna use these later. Did someone want to ask a question just now? Okay, let's put questions in the chat and I will go through the materials on the slides with you. Remember that we talked about superposition before. This is from last week. We had some examples showing we can have different numbers of qubits, and then that would determine how many configurations we will have. So remember, if we have one qubit, it can have two states in superposition. If we have two qubits, then we will have four configurations in superposition. If we have three, that would be 8. So n qubits will have 2 to the n possible configurations. It scales exponentially. So that gives us a degree of freedom to manipulate our system. Remember when we talked about interference last time, when we have superposition enabled interference, that was one of the strange things about quantum mechanics. Now, because of superposition is possible in quantum mechanics, there's yet another strange thing. Today is entanglement. So what is it? If we have a 2-qubit system, we would have 4 different types of configurations. That also means that we could have define certain configurations to be in superposition. So there are 2 very interesting special states that we can put the system in. If we have the 2 qubits in the same either 0 or 1, we have this option to have these 2 in superposition. So your first qubit could be 0, second qubit could be 0, or plus the superposition of the first qubit being 1 and the second qubit being 1. So this is one possibility. And another possibility is that they are different. So first qubit and second qubit are opposite, then you could have a 0, 1 plus 1, 0 state. So it's basically this 4, but then you can assign B and C to be 0, or A and B to be 0. So you get these 2. And why is it special? So look at this then. If you want to do an experiment, you just look at one qubit, say the first qubit, if you measure it to be 0, then you don't have to do a measurement of the second qubit. You already know your second qubit would be 0. Because each of this is represented with an amplitude. We remember it's squared is the probability. If your first qubit is already 0, you know there's no possibility that you will have this configuration. So you would know that your second qubit must be 0. You could do the same thing with your second qubit. You just measure the second qubit, you would know what your first qubit would be. And in this case, similarly, if you have an entangled set, then if you measure your qubit to be 0, first one, then you know your second one would be 1, and vice versa. This is called entanglement. Basically means the qubits are correlated. When you do the measurements, their results will be correlated. And we have four special entangled states when you have 2 qubits. These are called the Bell states. It's showing you that, so plus or minus of the 0, 1 and 1, 0 combination, or a plus or minus 0, 0, 1, 1. So the special thing about it is that the amplitude here now is equal. So it's equally likely to get the either outcome. So if you take these as an example, if your first qubit, when you do the measurement, is 0, just pick one of the states. For example, this one with a plus. Then you know you would definitely get a second qubit to be 0 with the probability of half. And remember, why do we have a square root here? Because of the normalization condition, we have to make sure that all the probability add up to 1. So when you have two states in superposition, that will be a square root of 2. And if you measure your first qubit to be 1, then it's not possible to be this one. It will be this one here. So your probability will be half to get 1, 1 state out. So again, this is a repeat to say that if you measure one qubit, you would know the other qubit without even looking at it. And mathematically, what does entanglement mean? We can write everything out nicely into this vector, which we introduced in the first class. So remember that if we had 2 independent qubits, how you represent the system is to do a tensor product. So these could be your 2 qubits, and you do a tensor product to write out your resulted vector, 4x1 vector. And that is to say, if you have 2 separate qubits and you put them together, they could form a system using a tensor product. But if you already have 2 qubits that's entangled, it's impossible to break them apart into 2 independent qubits. So if you try to equate this 4x1 qubit, this is one of the Bell states, and then equate it to a representation this way, you would never get a solution. It's impossible to write this state, the Bell state, into a individually separated 2 qubits. So that's how you can also test if something is in entanglement, is that once they are entangled, they cannot be separated into 2 independent qubits anymore. There is a very common mistake when people talk about entanglement. It always sounds very strange when people say, if we have qubits entangled, you can separate them infinitely far away, and if you change one of them, the other one would automatically change. That's not right. That's not true. That cannot happen. That would imply that information can transfer faster than light. You have two qubits infinite far away. If this one changes and the other one immediately feels the change and change itself, that's a information transfer. That's prohibited. We know that information cannot travel faster than light, but so many people talks about this when they mention entanglement. So next time if they say this, then you know that they don't actually understand quantum mechanics or quantum computing. So the picture of measurement the concept of measurement has to be in the picture, or at least you know that what entanglement implies is a correlation between your qubits. So what happens is when you have two entangled qubits, if you poke this one, that's what I was trying to show, is the other one doesn't feel anything. And if you separate them far apart, nothing is changing because the two qubits are still correlated. The correlation and entanglement is not a function of distance. So if you do a measurement of your qubits infinitely far away, you would know the answer to the other one without looking at it. That's what it is. That's all it is. There's no spooky interaction, as people say in popular science. There's just no interaction. If they are entangled and separated, then nothing is changing. So we can use this to make useful things. If you can prepare a pair of entangled qubits and separate them to two different people, one of them, if they take a measurement of their qubit, they can know what the other person will get when they make a measurement. So here, Alice and Bob prepared a pair of Bell states. They separated them, and Alice, if she measures and gets 0, she knows if Bob measures, he will get a 1, because the state will be in this one. Now, if she wants him to obtain 0 instead, she will just ask him to flip his qubit. And there are ways to flip qubits, which we'll talk later. So this is basically what entanglement implies. It's very, very useful. We actually use it in every single algorithm. So this is repeating the idea there. You start with one of the entangled pair. Alice makes a measurement, and she would know Bob has a particular 1. And if Bob measures his, he would know what Alice has. And if we can entangle 2 qubits, there's no reason we cannot entangle more qubits. So a Bell state counterpart for multiple qubits is the GHZ states. When you have 3, this is the simplest form of GHZ states, is these 111 and 000 in superposition. And if you have n qubits, you can just have many of them and put them into this particular state to entangle them. So this is a shorthand mathematical way to write this. You can imagine, even though it cannot communicate, it cannot be used to communicate information faster than light, it can still be useful. For example, in encryption, you would know if you establish a key using entangled qubits, you know what the other person will have. So you can encrypt your message and decrypt your message using a specific sequence. And some other examples also include teleportation. This is one of the ways to demonstrate if you have entanglement between your qubits, but it also is a way of communication. So I just said that they cannot be used to communicate faster than light. So there needs to be some information that's transferred using classical ways of communicating. So I'm not showing you any details of this algorithm yet. I'm just using this to tell a story with cartoon. We'll go into this to see this step by step once we learn how to manipulate qubits. So just look at this picture here. What is happening is when Alice and Bob, they prepare a Bell state, they separate them and they go as far away as they want. Then Alice now has 1 qubit, but if she wants Bob to know about some unknown qubit that she later obtains, she can actually entangle her now 2 qubits, and then she can do a measurement of her qubits, and she finds out the answer and call Bob, not directly telling him what she has, but telling him what to do with his qubit. When Bob does the measurement, he will get the same new qubit that Alice obtained using his only qubit. So that's what teleportation is about. It's basically because with a starting point, any of the Bell states, you would be able to build out a table, a grid of what to do to Bob's qubit. You know everything in between in this grid, and you can just do a manipulation to Bob's qubit to obtain what Alice wants him to know. We'll go into this what are X and Z later. These are gates. That's the way to apply a change to a qubit. So that will be our next few sessions, is about how you can manipulate qubits. Another similar algorithm is the superdense coding. It's kind of the opposite. So what just now Alice and Bob did was they exchanged classical information in order to exchange quantum information. So they did not directly send qubits, they sent classical information by calling Bob or sending him a letter. But in effect, Bob gets the quantum information Alice wants him to know. Superdense coding is kind of the opposite, where they were sending quantum information, but what Alice wants Bob to know is a classical piece of information. So again, you have to know what type of gate. You have to establish a table of possible outcomes. When they prepare a entangled pair, Alice can then come up with a way to let Bob obtain her classical information by sending him her qubit after she does a manipulation on her qubit. So Bob can obtain like classical information like 0001, 1011. It is called superdense because they are sending 1 qubit, but then it contains information of 2 classical bits. So this is another place where entanglement is used. So I'm just showing some of these simple kind of toy models to show that they are useful if you can come up with clever algorithms. And entanglement is used in every algorithm we're going to talk about. And coming back to this multiple qubits, I just want people to absorb this here. If you have n qubits, you can entangle them all. And if n equals to 5, that would be 2 to the power of, if n equals to 500, that would be 2 to the power of 500 possible states your system could be in. The total is more than the number of atoms in the universe. Yet, only 500 qubits are needed to contain all these information if you entangle all of them. And that's what nature has been doing. That's what our universe is having a lot of fundamental quantum particles that are in entanglement, and they are just doing this calculation behind our back. When we do an observation, we used the term collapse last week, but it's really a result of interference. We are making an observation to find out what's the most possible outcome, but then at the same time, all these particles are doing their own thing without us looking. So that's really cool. And then the last piece is a word of caution here, is that entanglement can be very useful if we know what we're doing. If we establish an algorithm that we know each step what the qubits would do, then we will get the results very efficiently. If we do one measurement, you would know what the rest of your system will be at. But entanglement can be also very dangerous because your system has to be perfectly isolated. If you prepare this very nice entangled system, you want them to be totally uninterfered with your environment. If there's any imperfection, it could very easily entangle with its environment. And the environment is also made up of all those quantum particles. So you have to have prevention. But then measurement is an act of destroying your system. So because all of the measurement devices are made of physical things and they're all at the fundamental level quantum, then when you approach your system with your measurement device, it would be entangled with your system as well. So you have to build in this mess up in your measurement in order to get the correct information you need. So there's a huge field about error correction. When you do measurement or you have unintended errors when the qubits entangle with its environment, you have to be very, very careful and have additional circuitry built in to correct the errors that could be caused by the environment. So we will also talk a bit more about this in the hardware sessions because different types of hardware will have different tendency to its entanglement with its environment. So that's what we're gonna show today. What time is it? And I think we can discuss and answer some questions. Let me get back to Teams now. I think my oops, is all blocked here. Okay, here. All right, let's see if we have any questions here. What are some of the methods to prevent errors during measurement? Yeah, so we'd cover it. It's also a field of very extensive research, and I'm not an expert in error correction, so I'm also learning. but we have to build extra. So some systems rely on multiple qubits to correct their errors. So you may have to build multiple qubits in order to do a calculation. Only one qubit is needed. And then there's different ways to counteract that mess up. So we can cover it a bit more once we talk about hardware. Do quantum entanglement violate uncertainty principle? No. Why would that be? If we measure the polarity of one particle and position of another, is it possible? I have not thought about it this way, but it doesn't have, is two different concepts. So entanglement is when you can put your qubits in certain combination, in a certain configuration. And that configuration would be one of your qubit, one of your physical hardware parameter, like a spin, or is, I'm just making it up now because you can make all kinds of qubits, or the energy level it is at, or perhaps its phase, the phase of the spin, or I don't know if any, perhaps position could be a parameter, but it would be one of the parameters you choose to use as your 0 and 1, and is only a interaction, interaction is a bad term, but is only a correlation between those parameters. So we don't have here like things like position or velocity is a different, uncertainty principle is a different concept here. So let me think about it a bit more to see how I can answer that a bit better without delving into physics. But super cold environment and magnet. Okay, that is to answer error correction. So you are definitely trying to reduce noise by cooling things down. And magnetic shield, if your particle or your system is subjected to magnetism, then yeah, you need to shield it. That's what we mean by isolation. So you have to first physically prevent your particles to interact with the environment. But there are additional things that you have to consider when it comes to doing a measurement, because all your, even if you cool it down, your whole fridge or your whole probe is a environment, is a part of the environment. So it could still interact with your system. So if I may add, measuring polarity does not mean measuring momentum. Yeah. When n qubits, and we're not necessarily using polarity for qubits anyways. So when n qubits are in uniform superposition, are they not unentangled? Uniform, what does that mean, uniform superposition? You mean when they have the equal amplitudes? Yeah, okay. They are not necessarily unentangled. So look at the Bell states a bit more. What entanglement really is just a correlation between the qubits. If you know the information of one of them, you would know the other. Doesn't matter what amplitudes they have, because you can intentionally put your two qubits in entanglement with the same amplitudes. So when you're talking about 500 qubits, what they entangled qubits? Yeah, they could be. When they entangle, then you have all those correlations going on, but we would never know until we do a measurement. So it's the calculation for the computation for quantum computer really is both using the entanglement and the superposition, which introduces interference. Let's see, is there any other question before? Okay, I think I started from the first one. With two entangled qubits, and by the way, people can use their microphones too, now that I stopped sharing. With two entangled qubits, the possible states go down to only 2 of the 4 possible. Yeah, that's a good way to say it. So I was trying to avoid using the term collapse, but sometimes it's easier for people to see it that way. Is you kind of eliminate one of the or 2 of the possibilities out of the 4 possible states.
That's why I was thinking in your example of the 500 qubits, being able to represent so many possible states. If they were all entangled, wouldn't, no matter how many they are, wouldn't they just represent 2 states, either all off or all on?
If they are qubits, yeah. So each one of them is either 1 or 0, but then they can all be entangled, meaning that they can all be correlated into one system and not being able to separate. Then if you do one measurement, you will get one outcome, but that's a result of all of the states in superposition.
Oh, I see. So the Bell states are more flexible than I thought. It's not just whether they're the same or opposite, but those 500 qubits have some entanglement that indicates some relationship, but not necessarily that they're all off or they're all on.
Right, yeah. So the GHZ states, those are called the maximally entangled states. So that's why the first configuration is all 0, the second configuration is all on. But there are they can entangle in many, whatever combination they have.
Okay, thanks.
Yeah. Is there any more questions?
Yeah.
We can.
So, can you hear me?
Yeah.
Yeah. I have a question that's just a tiny bit more advanced than what we've done today. Should I bother to ask it now or wait until some offline?
Yeah, we can hear it. Yeah, it can also help us know what we should talk about later.
So let's say I have 3 qubits, and I want to create an arbitrary vector, an arbitrary state for those 3 qubits. And so that would be eight elements in a column, right?
Yeah.
The question is there an easy way to figure out how to make that with the sort of most basic gates?
You don't even need to use gates to put them into any state. You can just have 3 qubits and write them out as 3 2x1 vectors in tensor product.
Yeah.
And then you get an 8x1. And there's no gates involved. Because what you are getting, the 8x1 vector, is a description of your state. So only when you want to.
I want to know how to work backwards. I want to get a particular 8, a particular set of 8 numbers. And I guess and I want to figure out how to make that with wires. And it's all, weird things with everything in different phase and so on and so forth.
I don't quite get your question. You
Okay, all right.
you mentioned wires.
What?
What kind of, you mentioned wires? What kind of wires?
So I want to figure out how to apply things like Hadamard and controlled knot
Yeah.
in order to achieve a certain state with say 3 qubits.
Yeah.
Is that an easy, intuitive thing to be able to figure out, or is it difficult?
In hardware? In hardware?
Not in hardware, just in terms of just simulations, just dragging and dropping.
Yeah, mathematically that's very simple. If you want
Okay,
to see, I have some later slides I can show you.
that would be excellent.
Yeah, so actually my next session, so starting this week, I will start talking about gates.
Yeah.
And it's all about putting matrices in front of vectors. So mathematically, that's very easy. If you want to put a certain qubit in any state, you can apply a certain gate to it.
Okay.
So yeah, so Hadamard gate is a 2x2 matrix, and you can just apply it to any of your one qubit and get the result.
Right. Yeah, that's not exactly my question, but I don't want to press my luck right now, so I'll wait. I'll be patient. Thank you.
No worries. Yeah, you can also post questions on the Hackaday project, and we can get to it later.
Okay.
Great. Thanks. Okay, I think that's it for today. If there's no more question, we'll have this recording posted on Hackaday. I'll see if we changed to team, so I think it's still a link I can share. And the slides will be there too. Thanks, everyone.
Thank you.
Yeah, see you next time. Bye.
Yes, thanks. It was great. Thanks.
Thanks.
Thank you.
Everybody leaving? People are here.